Hello everyone, welcome to Gate Academy Global. Academy. So now we will see workbook question. So let's see workbook question number 1. If the ratio of diameter of rivet hole to the pitch of rivet is 0.25, okay, so the ratio is given, that is of diameter of rivet hole dh and the pitch of the rivet, okay, and this is 0.25, then the tearing efficiency of joint is, so it is a very formula based question. We know that the tearing efficiency, will be 1 minus d by p into 100%, okay, this will be the formula, okay. So this will be 1 minus 0.25 into 100%, that is 75%, or you can write 0.75. If you don't want to represent in percentage, then you will be writing 0.75. So this will be the tearing efficiency, okay. So according to this, option number B will be the right answer. Option number B will be the right answer, okay. So this is very fundamental question, and if you want to recollect the concept that how can we calculate the tearing strength, so this was the part of the theory lecture. If you are confused that how can we calculate the tearing strength, so that is discussed in very detail in your theory lectures, okay. So if you have any doubt, just rewatch that video and just recollect every information, okay. Now let us see workbook question number 2. Workbook question number 2. So in workbook question number 2, this is a different type of question. It belongs to GATE 2010, okay. So here the problem is this type of loading is generally observed in a threaded joint. In riveted joint, such kind of loading condition will not be there, okay. But okay, it is okay that such kind of question is there, there is no problem. We can analyze this question, just analyze the effect of the load acting on the rivet, okay. So according to the question, this is a bracket like this, okay, and the loading is shown in the figure. So okay, this is the rivet, this is the rivet connection, okay. The dimensions etc. are given. We will see that whether there is any need of the dimension or not. I will be telling you everything. Now here is the point load of 1000 Newton, Now this distance is basically 32 mm, this is also 32 mm, okay. The distance from the base is 0.25, this is 0.25 mm, 2.5 mm, okay, 2.5 mm, and this is 7.5 mm, okay, this distance is 7.5 mm. So from the lower edge, this is lower edge, the distance are 2.5 and 7.5 mm. The size of this plate, okay, is 100 mm, and the diameter is not up to scale. So don't worry that what are the different situations, the data or the dimensions are not matching, okay, there are no proper ratio of the dimension, okay. It is just to just entitle the every dimension of the rivet. Now here you can see, as this bracket is connected to a wall, if you want to draw the side view, then you can analyze the connection. This is the bracket, okay, which is being connected to a wall through a riveted connection, okay. So let us say this is wall, this is wall, this is wall, and here we have rivets, okay, here we have rivets. So there is a rivet like this, okay, passing through the bracket and the wall. Now the rivets are subjected to various types of load. As you can see that this is the centroid, okay, this is the centroid, okay. We can calculate the value of centroid, but there is no need, okay. So just discuss, this is the centroid of riveted connection. Let us see. Now the load is eccentric, actually this is the load which is equal to 1000 Newton, okay. So this is eccentric, and this distance which is 20, okay, this distance is 20 mm, this distance 20 mm. So this 20 of eccentricity, this is E, this is the eccentricity of the load, okay. Now what will happen, due to such kind of loading on the riveted connection, there will be two types of stresses, okay. first of all, in order to support the applied load, the rivets will be giving you an upward reaction. Okay, so there will be upward reaction in the rivets, okay, and the load will be transmitted to the rivets like this, okay, and there are two rivets in a row. We have drawn the side view, and hence you must understand that there are two rivets in a row. So the load which is acting in downward direction, first of all, it will be divided into the number of rivets. Okay, it will be shared between the rivets. Now, as you can see in this diagram, this plate and this plate is having same width. Okay, this is also 32 plus 32, that is 64. So basically, you can see that the line of action of load is exactly perpendicular with the centroidal axis of the rivet. Okay, hence the load acting in downward direction will be equally distributed between the number of rivets. So there will be a primary shear stress due to this load, and also you can see that the bracket will try to tilt about this lower edge. Due to the external load, this bracket will try to rotate. That means it will tilt with some angle after a load is applied. Okay, and due to this tilting, you can see that the bracket will look like this after tilting. Okay, this will look like this. Okay, so there will be an extension in the rivets. There will be extension in rivets like this, and it is observable that the rivets which is closer to the lower edge is undergoing a very small value of extension, but the rivet at a large distance from the lower edge are having a high value of extension. So the extension over here is low as compared to this rivet. Okay, now due to this extension, a tensile stress will induce, and here we are avoiding the bending of the rivets. We are avoiding the bending, okay, because this diagram has been drawn in a very exaggerated manner. Okay, so you will be thinking that there will be bending also, but here the tilting of the bracket will be very small, hence we can avoid bending stress. So under such condition, the rivets will be subjected to two types of stresses. One is the shear stress and second is the tensile stress. So here you will be having shear stress, or you can also call it direct shear stress, and you will be having tensile stress, okay, due to tilting of bracket. Okay, now as I have told you that the line of action of load is exactly perpendicular to the centroidal axis, hence the external load will be distributed among the rivets equally. Okay, so there will be equal distribution of load. So the load acting on the rivets, is equal to shear force on a rivet. Okay, so shear force on a rivet will be equal to the load divided by the number of rivets. Okay, so there are 4 rivets in the connection and we are having a total load of 1000. So this will be 1000 divided by the number of rivets, that is 4. So each rivet will be subjected to a load of 250 Newton. Okay, so this 250 Newton is the shear force, or you can say direct shear force, or you can say primary shear force. The direct shear force is always considered as a primary shear force, and the shear force due to some different reasons like twisting, or you can see the external moment applied on the connection, that is known as secondary shear force. So the shear stress due to direct shear force is known as primary shear stress, and the shear force is known as the direct shear force. Okay. Now due to tilting of the bracket, we will be seeing a tensile stress. Okay. So tensile stress will directly proportional to the distance, distance of rivet from lower edge. Okay. Now as each and every rivet will be having same cross sectional area, then you can also say that the load acting on the rivet due to this tilting will be directly proportional to the distance r. Okay. So let us say this is distance r, or let us say this distance is L. Let us take it L. So L distance is this. Okay. This is distance L. Now this is the first row of rivets, second, third, okay, and third, and these are second and fourth. This distance is L2, this distance is L1. Okay. So the load P1, or you can say this load, let us say that shear force is P dash. Okay. So let us take this as P double dash. Okay. This load will be the P double dash. So P double dash is the tensile load, okay, on the rivet. So P double dash is tensile load on a rivet. The solution of question is very small, okay, but I am telling you the entire concept for such condition. You can directly solve the problem, but I am telling you some important concepts so that there will be a better understanding for such type of problem. As I have told you, this is not the conceptual problem belonging to a rivet, but in examination a riveted connection is given, whereas such under such kind of loading condition we will be using a threaded joint, we will not be using the riveted joint. Okay, but there is no problem. So now this load is directly proportional to L. Okay. Now what will happen, as you can see that the external load is trying to tilt the bracket. So in order to stop the tilting, the rivet must produce a resisting moment. Now this resisting moment will be produced about the lower edge, so that the summation of moments about the lower edge will be equal to 0. Okay. So let us say that the resisting force induced in the rivet number 1 and rivet number 3 is P1 and P3, and here in rivet number 2 and 4 the resisting force setup is P2 and P4. Okay. So the resisting moment, okay, you can see that about the lower edge, these force will produce an anti-clockwise moment, and the external load is producing a clockwise moment. So this is P into E is equal to P1 into L1 plus P2 into L2 plus P3 into L1 plus P4 into L2. Okay, this will be the equation. Okay. Now as you can see that P double dash is that this will be P1 double dash, P2 double dash, P3 double dash, P4 double dash. Okay. Okay, that is the load setup due to the tilting. Okay. Now this is that is P1 double dash will be directly proportional to L1. Okay. That means if you remove the proportionality sign, you will be having P1 double dash as C into L1, P2 double dash as C into L2, P3 double dash as C into L3, okay, and P4 double dash as C into L4. Okay. So from here you can write P into E into P1 double P equal to C into L1 plus C into L2 plus C into L1, okay, into L1 plus C into L2 into L2. So this will be 2C into L1 square plus 2C into L2 square. Okay. So from here we can have value of C as P by E divided by 2 L1 square plus 2 L2 square. Now we can also calculate the force setup in the force setup in the rivet, force setup in rivet, okay, due to tilting due to tilting of bracket as P1 double dash, okay, is equal to C into L1. So this will be equal to P into E divided by 2L1 square plus 2L2 square into L1, okay, and this will be equal to P3, okay, and P2 double dash will be equal to P4 double dash, and this will be P into E divided by 1 plus 2L2 square into L2, okay. So this will be the concept. Now this particular rivet will be subjected to a tensile stress and a shear stress like this, okay. The cross sectional area is pi by 4 d square. This is the cross section area. So as the tensile force is P double dash and the shear force is P dash, so the shear stress will be P dash divided by pi by 4 d square, okay, d square, and the tensile force tensile stress sigma t will be equal to P double dash divided by pi by 4 d square, okay. You can put the value of P dash and P double dash according to the most critical rivet, and the most critical rivet will be the rivet. As you can see that in each and every rivet the shear stress will be the same. Why? Because the shear force, the primary shear force, or you can say the direct shear force in each of the rivet is same, hence the shear stress in each of the rivet will be the same, but the tensile force on the rivets are different. Here the row of the rivet which is far from the lower edge will be having higher value of tensile force, hence they will be subjected to higher tensile stresses, okay. So here we will be using the higher value of the stresses, higher value of the stresses, okay, these stresses. So put the highest value of direct shear force and the highest value of the tensile force on the rivet, okay, and then you will be getting the state of stress, as this will be sigma and this will be tau, okay. Then solve the problem using any theory of failure, as here you can write the principal stress for the rivet as sigma 1 or sigma 2 equal to sigma by 2 plus minus root over sigma by 2 whole square plus tau square, okay. So this will be on adding up these values you will be getting the maximum principal stress, and on subtracting these values you will be getting the minimum principal stress, okay. Now also you will be calculating the value of maximum shear stress, okay. So maximum shear stress or in plane shear stress, okay, will be equal to tau equal to root over sigma by 2 square plus tau square, okay. Now from the current state of stress, as there is only one normal stress and all the stresses, that is all the normal stresses are 0, okay, all the normal stresses are 0. There is only one there will be only one principal stress which is non-zero, all the principal stresses will be 0, okay. So for this you can draw, all the principal stress will not be 0, there will be only two values of principal stress, the third will be definitely 0 because this is reduced to a plane state of stress, okay. So there will be two values of principal stress. So this is sigma and this is tau axis, okay, we will be drawing like this. This is the plane, of the loading like this. This is, let us say, plane A, this is plane B, so this will be plane A, okay, and this is the state of stress for this is the state of stress of plane A, okay, and for the other plane, that is plane B, there is no normal stress, so this will be the location of plane B like this, okay. Then you can draw the Mohr circle and you can see that there will be a positive value of sigma 1 and a negative value of sigma 2, okay. Now this is the maximum principal stress, okay, and as you can see that this is the positive value and this is the negative value, this is the positive value, sigma 1 will be positive and sigma 2 is negative, and this is a plane stress condition. So definitely the third stress will be 0, Okay, so this is the third stress which is 0. So out of the 3 principal stresses, one is positive, other is negative, and the last one is 0. So this will be the maximum. The 0 value will be the intermediate. The 0 value of principal stress will be the intermediate principal stress, and the negative will be the lowest principal stress or the smallest principal stress. And as I have told you in the theory lectures that if you draw Mohr circle between the greatest value of principal stress, that is algebraically highest value of principal stress, and algebraically lowest value of principal stress, then you will be getting the largest Mohr circle, and the radius of largest Mohr circle will lead you to the absolute tau max. So this will be absolute tau max. Absolute tau max. Okay. So from this relation only, it is proved that you will be getting tau max absolute. Okay. Now, if this is tau max absolute, then if you are using maximum shear stress theory, theory, tau max should be less than equal to tau permissible. Okay, and hence you will be able to solve the problem. And if you are using maximum distortion energy theory, as per maximum distortion energy theory, this will be root over sigma 1 square plus sigma 3 square minus sigma 1 into sigma 3, okay, should be less than equal to SYT divided by factor of safety. Okay, here sigma 1 is the maximum principal stress, okay, maximum principal stress, and sigma 3 is the minimum principal stress. Okay, and if you are confused a little, as here we generally use the formula of principal stress in this form. Okay, so let me tell you one thing, that this will lead you to the maximum and minimum value of principal stress only for this particular case, as this is a case of a plane stress problem, and the normal stress in the state of stress is acting only along one direction. So from Mohr circle it is very clear that the one principal stress is coming out to be positive and second will be coming out to be negative, and from this equation if you use positive sign for the first time and the negative sign for the second time, then at the very first time you will be getting the positive value, that is sigma 1, and at the second iteration, that is on using negative value, you will be getting this answer, this as a answer. Okay, and as per our consideration, sigma 1 is the maximum principal stress, algebraically maximum principal stress, sigma 2 is the intermediate principal stress, and sigma 3 is the algebraically lowest principal or the minimum principal stress algebraically. So I have mentioned everything in the Mohr circle according to the algebraic maximum or minimum. Okay, but from here also you will be getting the maximum and the minimum value. So if you want to avoid any complications, then you can say that sigma 1 obtained from this equation will be the highest value and this will be the lowest value. So sigma 1 will be highest and sigma 2 will be lowest, and if you follow the proper notations, that is sigma 1, sigma 2 and sigma 3, then the intermediate state sigma 2 will be equal to 0, as you can see from the Mohr circle. So this can also be written as sigma 1 and sigma 3, that is the maximum and minimum, and this will be followed for this particular case only, because in many cases this will be leading you to the greatest value of the principal stress and the intermediate value of the principal stress. Okay, that was the part of very first lectures in the theory of failures. You can find that if you have a biaxial state of stress like this, if you have a biaxial state of stress like that, this is sigma x, this is sigma y, okay, this is tau xy, then you can use the formula sigma 1 2 equal to sigma x plus sigma y by 2 plus minus root over sigma x minus sigma y by 2 whole square plus tau xy square. Okay, this is tau xy. Now, one thing should be very clear, that using this formula you may get two positive values. Okay, you will be considering the positive sign for one time and second sign for the negative sign for the second time, and then you will be getting sigma 1 and sigma 2. Now, if sigma 1 is positive and sigma 2 comes out to be negative, okay, and it is a plane stress problem, that means the stress on the z direction, normal stress on the z direction is 0, then definitely this will be the highest principal stress, that is the greatest principal stress, and this will be the lowest principal stress, because being a plane stress problem, there will be the third principal stress will be 0. Okay, so algebraically talking, this will be the highest value, 0 will be the intermediate value, and then the negative value will be the lowest value. Okay, so if you use the proper notations, then you will be writing it like sigma 1 will be your highest value, okay, highest, okay, then sigma 3 will be the lowest value, that is negative value, and sigma 2 will be 0 value. Okay, but from this equation, if you are getting two positive values or two negative values, so in that case the situation will be different, and that is discussed in the lectures of chapter number 1 in very detail. Okay, so just remember that this will not be giving you the greatest and the lowest principal stresses all the time. There are some foundation to it. Okay, if this equation is giving you two positive answers, then the third principal stress will be 0 in case of plane stresses. If this is giving you two negative answers, sigma 1 is coming out to be negative and sigma 2 is also coming out to be negative, then what will happen? Then third will be 0 for a plane stress problem. If this is giving you a positive value and a negative value, then in this case the maximum principal stress will be the positive value, and the minimum will be the lowest value, and the intermediate stress will be the 0 value. Okay, but in case where it will be giving you a two positive values or two negative values, in case of two positive values, the magnitude wise or the algebraically positive value will be the highest principal stress, and the 0 will be the minimum principal stress. Okay, so if it is giving you sigma 1 in some positive value, okay, and sigma 2 some another positive value such that sigma 1 is less than sigma 2. So this is not the maximum, this is not the minimum principal stress, this is not minimum principal stress. Okay, minimum principal stress, this is not minimum principal stress, as being a plane stress problem, okay, sigma 3 will be 0 and this will be the lowest value. So this sigma 3 is minimum stress, minimum principal stress. So always remember this concept, because these concepts confuse the students many times. Okay, now put all the values in this equation and you will be solving the problem. So this will be the entire concept for such kind of loading. If there is another question from GATE examination for such types of loading of Rivet, but let me tell you one thing, that this is not a possible case of loading for rivets, because generally for such condition we will be using threaded joints, not the riveted joints. But if in GATE examination, if in GATE 2020 or in GATE 2022 or in any GATE examination for future, if such kind of question is there, then you must understand the entire concept from this lecture only. Now let us come back to the question. So according to the question, we have to calculate the direct shear stress only in megapascal. So the direct shear stress will be due to the direct shear force, okay, and the direct shear force will be equal to P divided by N. P is the external load and N is the number of rivet. Okay, so we can calculate the direct shear stress. We can easily calculate the direct shear stress. So let us proceed to the answer. Okay, so direct shear stress tau will be equal to the primary shear force or direct shear force on a rivet divided by the cross section area of the rivet. Okay, this is the cross section area. Okay, and the diameter of rivet is 6 mm, and in case of a joint, I have told you that if there is a joint, then the diameter of rivet and the diameter of hole means same thing. Okay, so we can solve it. This P dash is equal to 250 newtons, okay, divided by pi by 4d, that is 6 mm square. Okay, so answer will come out in Newton per mm square. Okay, so this will be 250 divided by pi by 4 into 6 square. So this is coming out to be 8.84 Newton per mm square, or you can call it megapascal. Okay, because 1 Newton per mm square is equal to 1 Newton per mm square is equal to 1 megapascal. Always remember. Okay, so according to our answer, option number B, will be the right answer. Now let us see workbook question number 3. Now let us see workbook question number 3 and 4. Okay, so a single riveted lap joint of two similar plates as shown in figure below has the following geometrical and material details. So in diagram you can clearly see that the width of the plate is given. Okay, so in that case I have told you in the theory lectures that if the width of the plate is given, then the calculation must be based on the total number of rivets. So here we can see that 3 rivets are there in the joint, so we will be using the total number of rivet is equal to 3 for our calculations, okay, and that should be very clear. Now also I have told you that if you can read out the question, and it is written that a single riveted lap joint of two similar plates. So single riveted joint means there will be only one row, double riveted means there will be 2 rows, triple riveted means there will be 3 rows, and I have proved in the theory lecture that this single, double and triple, what it stands for the number of rivets per pitch, and in this diagram also either the width is given, but you can find out the number of rivets per pitch. So if number of rivets per pitch will be 1, hence it is a single riveted lap joint. Okay, now moving on, different data are given. The width of the plate is 200 mm. Okay, width of the plate is 200 mm. The thickness of plate T is equal to 5 mm. Okay, the number of rivet N is equal to 3. Okay, the diameter of rivet D is equal to, here it is mentioned as dr, but we take it as D, so I will be writing D only. Okay, so this is 10 mm, this is ds, the diameter of hole, dh is 11 mm. Okay, the allowable tensile stress on of the plate, okay, that is for plate the permissible tensile stress is 200, okay, is 200 megapascal. Okay, or this is also known as sigma T permissible. Okay, this is also sigma T permissible, that is permissible tensile stress. Now the allowable shear stress, that is tau permissible, or you can also write it tau allowable, is equal to 100 megapascal, and the allowable bearing stress, that is nothing but the crushing stress. Okay, so sigma C allowable, or you can write sigma C permissible is equal to 150 megapascal. 150 megapascals. Okay, now let us see workbook question number 3. So in question number 3, if the rivets are to be designed to avoid crushing failure, okay, the maximum permissible load P in kilonewton is. So for avoiding the crushing failure, the value of permissible load can be calculated by using the formula. As you can see that there are 3 rivets in the connection. Okay, there are 3 rivets in the connection like this, 1, 2, 3. Okay, so AC, that is area under crushing, or you can call it bearing area, and that is equal to the projected area. Okay, that is equal to the projected area in a thickness of plate, in thickness of a single plate only. Okay, I have told you that if we have 2 plates like this, and we have a rivet hole in which we have a rivet, this is plate number 2. The plate may have different thicknesses also. Let us say this is T1 and T2. Okay, this is T1 and T2. So in that case, the crushing area, okay, that is AC, that is the crushing area under crushing, is minimum area among minimum area between 2 values. Okay, so if this thickness is T1, this thickness is T2, such that let us say T1 is less than T2. Okay, and we have a rivet over here. The diameter of rivet, that is equal to the diameter of hole. As after being connected, the rivet will be filling the hole completely, hence the diameter of hole will be the diameter of the rivet after the joint has particularly formed. Okay, now for that situation, the crushing area, this will be the crushing area, let us say AC1, and this will also be the crushing area, let us say this is AC2. Okay, so this is crushing area number 1, crushing area number 2. So AC1 will be equal to the diameter DH, okay, multiplied by thickness T1, and AC2 will be dH into T2, and T2 is greater than T1, hence AC1 will be less than AC2. So this will be used for the calculation. Now if T1 is equal to T2, AC1 will be equal to AC2, that is area under crushing for the first plate, and for the second plate both will be the same. So we can go for any value. Okay. Now this will be equal to D into T, or you can write DH into T. Okay. So AC will be equal to DH into T if T1 is equal to T2. Now if there are number of rivets in the connection, then the total crushing area or total area under crushing will be equal to N into D into T, or if you write in terms of DS, so this will be N into DH into T. This will be total area under crushing. Now I have also told you in the theory lectures that there may be a situation where crushing of rivet will be asked, and for that you will be having separate value of the rivet pin and the rivet hole. The diameter of rivet and the rivet hole will be given in the problem separately, that I have told you in the theory lectures. Okay. So the rivet have two types of strength, that is a crushing strength and the shearing strength. Okay. If you talk about rivet only, okay, for rivet just make a separate note. Again, if you want to note it down with this numerical only, then you can also make a separate note along with the numerical, that for rivet you will be having, that is the load carrying capacity in shear, PS is load carrying capacity in shear, okay, and PC, that is load carrying capacity in crushing, okay, and the strength of rivet will be the lowest among these two. The strength of rivet is least between PS and PC, okay, PS and PC, whichever is the least value, that will be the strength of rivet. And if you talk about a riveted joint, for a riveted joint you will be having three strengths, that is PS, PC and PT. This is the load carrying capacity of riveted joint in shear, okay. This is load carrying capacity of riveted joint, RJ means riveted joint, in crushing, okay, and this is load carrying capacity, LCC, of riveted joint in tearing, and the strength of joint will be least of these three values. Strength of joint, or you can say riveted joint, will be least of PS, PT and PC, least of PS, PT and PC. This is very important to understand, and in this question it is not asking for the riveted joint, it is asking for rivets. It is not asking for riveted joints, and the calculation of the crushing load, okay, or that is the permissible crushing load, will be based on the diameter of rivets only, okay, and diameter of rivets is 10 mm, okay. So here in this question we have to calculate the crushing strength of the rivet only, not the riveted joint, hence the crushing strength or the load carrying capacity in crushing for rivet, LCC of rivet in crushing, will be equal to number of rivets into the diameter of rivets into the thickness of plate into the crushing strength or the permissible crushing stress. Clear? So if you want to calculate PS and PC, this will be based on the diameter of rivet. Always remember, this is the second time when I am telling you all these things, okay. So the calculation for PS and PC will be based on diameter of rivets if question is asking for rivet only, and if it is asking for riveted joint, then you will be going for DH, that is diameter of hole. So for riveted joints, for the calculation of riveted joint, we will be using the diameter of hole, okay, because we will be assuming that the rivet has completely filled the hole, okay. So n is equal to 3, the diameter of rivet is 10 mm, the thickness of plate is 5 mm, and sigma c permissible is 150. Here 150 megapascal is the value of sigma c, or you can also write it as 150 Newton per mm square, okay. So I am putting the value as 150 Newton per mm square. So let us solve. So this is 3 into 10 into 5 into 150. So this is 22,500, 2250 Newton. That means that is 22.5 kilonewton is the load carrying capacity in crushing, okay. This is the load carrying capacity in crushing. So according to our answer, option number C will be the right choice. So option number C is the correct option, okay. Now let us see question number 4. If plate has to be designed, now here it is talking about plates, it is not talking about the joint again. Now for plates, if the question is only for plate, so plate can have only a tensile stress, there will be no crush. If there is no rivet attached to the plate, then there will be only a tensile stress, okay. There will be only tensile stress, as I have told you in the part where we have discussed the tearing strength, okay. So if we have a plate, the width of the plate is W and the thickness of the plate is T, okay. So here the area of cross section, or you can say simple area, will be W into T, okay. So the area is uniform throughout and you are applying a tensile force P, okay. Now if it has a hole, then the stress induced in the component, or you can say in the plate, will increase, as here we have removed some material in order to form the hole. So this will be the total area available will be A equal to W, this is the width of the plate, W minus D into T, okay. And this area, let us say this is A dash, so A dash is less than A, okay, and stress is equal to P by A. So according to this, the stress here will be P divided by A dash, so sigma dash is greater than sigma, so stress will increase, okay. So the stress produced in the plate will be high, okay, if there is a rivet hole. Now the fundamental thing is that the load carrying capacity of the plate will be obtained from this diagram. So the load carrying capacity P in tension for plate, not for the joint, not for the rivet, for the plate only, this will fail due to tension, okay. There is only one stress, that is tensile stress, and if it is made up of ductile material, we will not observe any kind of failure, okay. But if compressive stress is very high, we will see the bludgeoning of the material, or there will be a buckling in the plate. If the plate is sufficiently large, then there will be buckling also, okay. So crushing will occur if there is very excessive tensile stress, there is very excessive compressive stress, but it will not generally take place for the plate, okay, as this is large in size. So crushing failure will be there if the load is very high. Now it will generally fail due to tension, so the PT will be equal to W minus D. Now D is what? D is the diameter of hole, so for hole the diameter of hole is written as DH, okay. So let me modify the value, this will be DH, so W minus DH into T will be value of A dash, so W minus DH into T into sigma T permissible, and this will be permissible tensile stress for plate, okay. And on solving we will be getting the load carrying capacity of plate in tension. This is the simple idea. Now let us solve the workbook question number 4. So for question number 4, now, so the permissible load P in kilonewton, W, that is width of the plate is 200 mm, so this is 200 mm minus the diameter of hole is 11 mm, the thickness of the plate is 5 mm, okay, into the permissible tensile stress for the plate, okay, and for the plate the permissible tensile stress is 200 megapascal, that is 200 Newton per mm square. So now on solving we will be getting the permissible tensile load for plate, okay, and this should be there to avoid the tearing failure of the plate. Okay, this is the load, that is the maximum load which the plate can carry without tearing. This is the maximum load, this is the value of maximum load which plate can carry, which plate can carry without failure. Also, after forming the riveted connection, the only stress due to which the plate will fail is tearing stress. Also, there is possibility of crushing of the plate surface near the hole. There may be enlargement of the size of hole due to crushing, but that will affect the joint. Okay, that will affect the entire joint, not only the plate. So, if I am talking about plate only, then we will consider only about the tearing stress. Okay, that is tearing of the plate will be considered whenever we are dealing only with the plate, and when we will be dealing with the joint, that is rivet plus plate. So, in that case we will be considering PS, PC and PT. Okay, and the strength of the plate will be the least among these three values. Okay, that I have told you earlier. Okay, so on solving, this is 200 minus 11 into 5 into 200. So, this is 189,000. Okay. Now, the number of hole, okay, number of hole is 3. So, multiply it by 3, okay, as this that is only for one hole. Now, if there is more than one hole, for a case where we have more than one hole, okay. So, in that case, like this, if this is the width of the plate carrying 2 holes or 3 holes, this is the width of the plate, okay, this is the diameter of hole DH. So, now the area or the critical area, or you can say the minimum cross section area, A minimum, or you can also call it A critical, or simply you can call it A, okay, area of cross section, that is least cross section over the discontinuity, okay, whatever you call it, this will be W minus 2 into DH. So, you can generalize the relationship for the area of cross section as, if N is the number of the rivet hole, then A minimum or A critical, okay, can be written as width of the plate minus N times of DH. Okay, this will be the area of the plate. Now, on multiplying it with the permissible stress, you will be having permissible tensile load on the plate. This is permissible tensile load, okay, or you can also call it, I am writing it here, okay, you can also call it strength of plate in tension, or you can call it the load carrying capacity of plate in tension, and this will be PT equal to W minus N times of DH, okay, into sigma T permissible, and this is for plate material. Okay, this is for plate material. Now we can see the workbook question number 4. As it's a common data question. So, here in question number 4, the plate is having 3 rivet hole. Okay, so as per the data given in the problem, it has 3 holes, and the diameter of hole is 11 mm. The width of the plate is 200 mm. So, we can write that the load carrying capacity of plate, okay, in tension will be equal to W minus N into DH into sigma T permissible. Okay, so width is 200 minus N 11, okay, multiplied by sigma T. The permissible tensile stress in the plate is 200 megapascal, that means 200 Newton per mm square. So, multiplied by 200 Newton per mm square. Okay, so now let us calculate. This will be 16700 Newton. Okay, now according to this, it can be also written as 167 kilonewton. So, according to our answer, the option number C will be the right choice. Now, let us see workbook question number 5. Now, let us see workbook question number 5. A horizontal plate has been joined to a vertical post using 4 rivets arranged as shown in the figure. Okay, so here we have 4 rivets. In the arrangement, here we have a bracket like this. Okay, so there is a load acting on the connection of 400 Newton. Okay, this is a problem of eccentric loading. So we have 4 rivets. Okay, and the dimensions of the arrangement are given. Basically, the center to center distance between the different row are given. So this is 40 mm. So this is basically the pitch, and this is, you can call it a back pitch. Okay, this 40 mm stands for the back pitch. Okay, this is the first row, this is second row, and the distance between the first and the second row will be the back pitch. Distance between 2 rivets in the same row will be the pitch. So this is basically P, and this is basically PB. Okay, but it is not required to understand these things in the problem. Okay, now the magnitude of load on the worst loaded rivet in Newton is. Okay, so we have to calculate the load on the rivet. Now there will be 2 types of loads. First will be the direct shear force, and second will be the secondary shear force. Okay, as you can see that this load can be replaced as this will be 400 Newton. Okay, and this will be creating a moment of 400 into this distance, that is 400 into E. The eccentricity is 500 mm. Okay, so 400 Newton multiplied by 500 mm, this is 20. Okay, that is 200 and a single 0, you can say this will be the torque, that is in Newton mm, or you can write it as 200 Newton meter. Okay, this will be the moment. Now this will be producing a primary and a secondary shear force. The direct shear force, which is acting at the centroid of the arrangement, will be producing the primary shear force, and that moment, okay, about the center of gravity, centroid of the arrangement, will be producing the secondary shear force. Okay, now the primary shear force will be the external load. Primary shear force will be equal to the external load, that is 400 Newton, divided by the number of rivets, that is force, that is 100 Newton. Okay, so this will be the primary shear force acting on each rivet. Okay, so this will be 100 Newton. Okay, 100 Newton. Now let us, this is 1, 2, 3, 4. This is the centroid G. Now as you can see, the rivets are arranged in a square geometry. Okay, so the centroid can be easily located. This centroid will be having a coordinate of 20 mm and 20 mm, as these rivets are arranged in a square orientation. Hence this square will be having centroid over here, and the side of a square is 40 mm and 40 mm. So center will be in 20 mm and 20 mm. This will be 20 mm, this will be 20 mm, and this will also be 20 mm. Okay, so this will be the location of centroid. Now as this is a square, the radial distance between the centroid and the centers of each rivets will be the same. Okay, so if this is R1, this is R2, okay, this is R3, this is R3, and this is R4. So R1 will be equal to R2, and it will be equal to R3, and it will be equal to R4. Okay. Now as this side is 20 mm, okay, and this side is also 20 mm. So using the Pythagoras theorem, you can calculate R1. Okay, that will be root over 20 square plus 20 square. Okay, so this will be 28.284 mm. Okay, now we can calculate the secondary shear force. Okay, so secondary shear force is equal to, if this is the primary shear force is P1 dash, P2 dash, P3 dash, P4 dash, and all will be equal, as we know from our theory lectures that primary shear force will be equal in every rivet, and that will be equal to the total load divided by number of rivets, so that is equal to 100 Newton. So secondary shear forces, that is P1 double dash or P2 double dash and P3 double dash and P4 double dash can be calculated using the concept that P is directly proportional to R, and as you can see the radial distance of each of the rivet with respect to the centroid is same, hence all the secondary shear force will be equal. Okay, so secondary shear force will be same. Now we know that this is equal to, this can be written as P equal to C into R, where C is the constant of proportionality. Okay, and the constant of proportionality will be having a value of P into E divided by R1 square plus R2 square plus R3 square plus R4 square. Okay, this formula was derived in the theory lectures. Okay, you can calculate the value of C. What will the value of C? Just by using the concept that is the external moment of external load, external load about centroid will be equal to resisting moment. Okay, resisting moment, as the secondary shear force is nothing but the resisting force which will be creating a resisting moment such that the effect of external load, that is the moment due to the external load, can be encountered. Okay, so this will be the direction of the secondary shear force. This is the direction of secondary shear force, and we know that the secondary shear force acts perpendicular to the line joining the centroid and the center of the rivet. Okay, so this will be P1 double dash. Okay, this will be P2 double dash. Okay, this will be P2 double dash. This will be P3 double dash, and this will be P4 double dash. Okay, you can make a separate diagram for them like this. This is P1 dash, this is P2 dash, this is P3 dash, this is P4 dash, this is G. Okay, then this is the line joining the center and the centroid. Then this will be P1 double dash, this will be P2 double dash, this will be P3 double dash, and this will be P4 double dash. Okay, now I have told you that for the rivets which have the minimum value of theta, what is theta? Theta is the angle between the primary shear force and the secondary shear force. If the theta is minimum, then the resultant will be maximum. Now as you can see, secondary shear force is same for every rivet, primary shear force is also same for all the rivets, and hence the rivets are arranged symmetrically. So this theta and this theta will be same, that is, if you call it theta 2 and this as theta 3, this as theta 1, and here this is theta 4. So theta 1 will be equal to theta 4 and theta 2 will be equal to theta 3, and these are the minimum value. Hence definitely the rivet number 2 and rivet number 3 will be the most critical rivet. Okay, so we just have to find out the value of theta, and either you can solve for rivet number 2 or rivet number 3, as both have same primary and secondary shear forces and same value of theta, so both will be giving you the same answer. So the resultant force on the critical rivet, as critical rivet is number 2 and number 3, number 2 and number 3 are the critical rivet. Okay, critical rivets, that is rivet number 2 and rivet number 3. Okay, so the resultant force, to find out the resultant force, that is R2 or R3, first of all let us find the value of theta. Okay, so as this is 20 mm, this is also 45 degree. Okay, this is 45 degree. Let me draw a separate diagram like this. This is G. Okay, this is the rivet number 2. Okay, this is P2 double dash, and this is P2 dash. This is 45 degree. This is also 45 degree because this is a right angle triangle. So this will also be 45 degree. Okay, so theta 2 will be 45 degree. Okay, and if you talk about theta 1, then theta 1 will be 135 degree. Okay, you can calculate the angle. This is the rivet number 1. This is the line joining the center and the centroid. Okay, this is the secondary shear force. This is 90 degree. As this is 45 degree, this will also be 45 degree. Then the total angle, that is theta 1, will be 90 plus 45, that is 135 degree. Okay, as there is no need to calculate theta 1, but I am just telling you the value of theta 1. Okay, so as theta 2 equal to theta 3 is equal to 45 degree, then R2 or R3 will be equal to root over P2 dash square plus P2 double dash square plus 2 P2 dash P2 double dash cos theta. Okay, so this will be P2 dash, that is 100 square plus P2 double dash. Okay, P2 double dash, let me calculate the value of P2 double dash. I have forgotten to calculate the value. okay, due to discussion. Okay, so this will be P2 double dash will be equal to C, that is P, that is 400, okay. P2 double dash will be C into R2, C into R2, okay. C is this value, that is P, that is 400 into eccentricity, that is 500, okay, divided by R1, R2, R3, that is all the values of R are equal, so he will be getting 4 R1. In this case only we will be getting 4 R1 square, okay, 4 R1 square, 4 times of 28.28 square, okay, multiplied by R2, that is 28.28. So this will be 400 into 500 divided by 4 into 28.28 square into 28.28. So this will be 1768.03 Newton. This is the secondary shear force, okay. So let us use the value over here. So this is 1768.03 square plus 2 into 100 into 1786, okay, 0.03 into cos 45 to cos 45, okay. So let us solve. So this will be 100 square plus 1768.03 square plus 2 into 100 into 1768.03 into cos 45, okay. So this is coming out to be, so this is 1840.09, or you can write 1840.1 Newton, okay. So as this is a numerical answer type question, so this will be your answer, okay. So in the verse rivet, that is rivet number 2 or 3, the force acting on the rivet will be 1840.09 Newton, okay. So this is the right answer. So we have discussed the workbook question and we have discussed some examples also on the riveted joints. So I think that the concepts will be here, okay. I have discussed every numerical problem in very detail, okay, but you should understand what is the proper procedure while discussing the things. Things may, you know, get shuffled, that I will be discussing numerous things along with the question, okay. So you must understand that what is the procedure, and the procedure will be very clear once you get the problem, okay. Just get into the problem, solve the question properly. In eccentric loading of riveted joints, there is only few things to be mentioned, that is, first is the primary shear forces. The method to calculate the primary forces is here, okay, and using this relationship you can find out the secondary shear forces as well. Then you have to find out the value of theta, and then you have to find out the resultant force on the element. That is the only thing which you have to follow, okay. Now we will be starting our next topic, that is the bolted joint, okay. Thank you.